Hello, today we're going to discuss titrations. So you have performed titrations before, at least if you've taken chemistry at TCC. So just as a refresher, in an acid-base titration, a solution of unknown concentration, which we call the titrant, is slowly added to a solution of known concentration until the reaction is complete. So a lot of the time we're performing a titration in order to determine the concentration of an acid or the concentration of a base. Now, when the moles of acid are stoichiometrically equal to the moles of base, the titration has reached its equivalence point. So the equivalence point, again, tells us the point at which the moles of acid are equal to the moles of base. So they have completely reacted with each other. Now, often we need a way to determine where the equivalence point is. So we're going to use something called an indicator. And this is a chemical that changes color when the pH changes. So we're going to cover all of these different concepts. So here's a visual of a titration. So typically we put the acid in the Erlenmeyer flask at the bottom. And typically we put the base in the burette above the Erlenmeyer flask. You can switch them, so you can perform a titration where the acid is in the burette and the base is in the Erlenmeyer flask, but it kind of depends on what you're trying to determine, and also it can depend on the indicator you're using as well. So initially, you'll have two colorless or clear solutions. So the acid will be colorless, and then the base up above will also be colorless. Now, again, we need some sort of indicator that changes color as base is added. And typically, the indicator that we use is called phenolphthalein. Oh, ran out of room. So phenolphthalein is clear in acidic solutions and pink in basic solutions. So if you have taken Chem 162 at TCC, then you have performed a titration before. And in that titration, we used phenolphthalein. So you did see that transition from clear to pink. So as we start adding base to our acid, we'll start to form water molecules, because remember, acid and base will neutralize each other. So I'll write off to the side the reaction between acid and base. The other way that you can write this is by using the hydronium ion instead of the hydrogen ion. And we get the same thing, but we can just write that we have two water molecules instead of one, and that will balance the reaction. So either way, we're producing a neutral product, which is water. And as we start adding base, you'll notice some color changes occurring. So some pink will start to appear. But if you swirl the flask, the pink color will disappear up until we reach the equivalence point. So remember, at the equivalence point, the moles of acid is equal to the moles of base. So it's at this point that we have a neutral solution. Okay. So what you saw in the first lab for this quarter, Mark Allen performed a titration and was able to produce what's called a titration curve. So a titration curve is a plot of pH versus the amount of added titrant. So in this case, added base. Now what you probably noticed is somewhere in the middle of this titration, there was a pretty steep increase in pH. And it's that steep part that tells us where the equivalence point is. All right, so in the graph on the bottom here, we have on the x-axis the volume of NaOH added in milliliters. And then on the y-axis, we have pH. Now, this titration curve is for a strong acid and strong base. So maybe we're adding HCl and NaOH, for example. So initially, in the Erlenmeyer flask, we have acid. So that's what we're measuring the pH of. So initially, and I'm going to change my marker color here, we have a pretty acidic solution. And as we start to add base, we haven't quite reached the point where the moles of acid are equal to the moles of base. So we do have more moles of acid. So the solution is going to stay pretty acidic up until we hit the point at which the moles of acid are equal to the moles of base. Now after this point, we're going to add more and more base, and we've already neutralized all of the acid. So now the pH just depends on how much base is present in solution, or excess base. Okay, so again, the pH of the equivalence point will depend on the pH of the resulting solution after we've added some base. Now remember that will be a salt solution, so if we write out the reaction of HCl and NaOH, remember that the hydrogen from the acid and the hydroxide ion from the base will team up to create water. And then whatever's left over will form our other product. Now that will be aqueous, so in this instance, sodium ions and chloride ions are floating around in solution. So this resulting solution is a salt solution. Now the equivalence point of a neutral salt will give us a pH of 7. The equivalence point of an acidic salt will give us a pH less than 7. And then the equivalence point of a basic salt will give us a pH greater than 7. So NaCl is a neutral salt. And remember from chapter 16, we saw some examples of acidic salts and basic salts. So I encourage you to go back and review what makes an acidic salt and what makes a basic salt. But the equivalence point makes sense, right? So if we have an acidic salt, we expect the pH to be a little bit lower than 7. And if we have a basic salt, we expect the pH to be greater than 7. Now, remember as well that beyond the equivalence point, the unknown solution in the burette is in excess. In this case, a base. So the pH is going to approach the pH of the base. So that's this portion here. Now, what if we flip our acid and base? So what if in the Erlenmeyer flask we have some sort of base, and then in our burette we have some sort of acid? Now, because we're recording the pH of whatever is in the Erlenmeyer flask, in this example, we would start with a really high pH. So we would start with a basic solution. And then as we start to add more acid, we'll see the pH slowly decrease until we hit the point at which the moles of acid are equal to the moles of base, the equivalence point. And then after that, because we've neutralized everything, we're going to add more acid, and that's going to be in excess. So now our solution pH depends on the acid. So we'll have something that's acidic. So if we flip our strong base and strong acid, we're also flipping our titration curve. So instead of starting out with something acidic, we're starting out with something basic. The equivalence point should be the same, and at the end, we'll have something that's acidic, so a solution that's acidic. So let's go through an example. We're going to calculate the initial pH of a 0.1 molar HCl solution, and then we're going to calculate the pH after we add certain amounts of sodium hydroxide. So in this case, sodium hydroxide is in the burette. And remember, sodium hydroxide completely dissociates into sodium ions and hydroxide ions. So we can just consider the hydroxide ions here. And then in the Erlenmeyer flask, we have acid. And we're just going to write H plus because we know that HCl is a strong acid and it completely dissociates into hydrogen ions and chloride ions. So let's calculate the initial pH of this solution. So we know that pH is equal to the negative log of the concentration of hydronium ions. And remember, hydronium ions are equivalent to hydrogen ions. So we're just going to plug in the concentration of hydrogen ions. And again, remember that hydrochloric acid completely dissociates or ionizes in water. So we end up with hydrogen ions and chloride ions. So if we're starting with 0.1 moles per liter of hydrochloric acid, that means that we also have 0.1 moles per liter of hydrogen ions after ionization. So we're just going to plug that value in and take the negative log of 0.1. And feel free to pause the video at any point if you want to try these calculations as we go. So you should have gotten a value of 1 for your pH. Okay, so that's our initial pH before we add any base to solution. So now let's calculate the pH after we add 5 milliliters of 0.1 molar sodium hydroxide. Now remember, sodium hydroxide is a strong base, so it's going to completely dissociate into sodium ions, and hydroxide ions. So if we have a 0.1 molar solution of sodium hydroxide, that means we have 0.1 moles per liter of hydroxide ions after dissociation. Okay, so let's figure out how many moles of acid we have and how many moles of base we have to start, because that will make things a little bit easier to perform some of our calculations. Now, the reason that makes it easier is we're changing the volume of solution after each addition of sodium hydroxide. So the concentration of sodium hydroxide and HCl will also change. So instead of having to deal with those changes in concentration, let's just deal with moles and then we'll calculate concentrations later. All right, so let's calculate how many moles of acid we have. So initially we're starting with, let's go back. Oh, I didn't tell you how many milliliters of acid we're starting with. So let's say that we're starting with 25 milliliters of HCl. Okay, so we're starting with 25 milliliters of HCl solution. And if we want to determine the number of moles of hydrochloric acid using the concentration, we need to convert milliliters to liters. So remember that there are 1,000 milliliters in every liter. And now we can use the concentration of hydrochloric acid to calculate how many moles of hydrogen ions we have. Okay, so after performing this calculation, we should find that we have 0.0025 moles of hydrochloric acid. And remember, that's going to equal the amount of hydrogen ions we have in solution, because hydrochloric acid completely ionizes. Okay, now let's figure out how many moles of base we're adding. So we're adding 5 milliliters of the NaOH solution, and this calculation is going to be very similar to the one we just did. Oh, my pen isn't working. There we go. And again, if you want to pause the video at any point and do this calculation on your own, you can. So we should get a value of 0.0005 moles of NaOH. And remember, that will equal the moles of hydroxide ions. All right, now we're going to make a table and we're going to show the changes in moles for each as they react. So I'm going to start by writing out again that reaction between hydrogen ions and hydroxide ions. And then before the addition of any hydroxide ions, we said that we had 0.0025 moles of hydrogen ions. And then we don't have any hydroxide ions. And we're not going to worry about water here because remember it's a pure liquid. So we don't include it in our consideration of concentration changes or pH. All right, so now we're going to add 0.0005 moles of hydroxide ions. And then after the reaction, we're going to see that all of the hydroxide ions react. And the change in the number of moles of hydrogen ions will be 0.0025, and then we're going to use up 0.0005 moles because we're going to have a one-to-one reaction between hydrogen ions and hydroxide ions. Okay, so what will be left over after that reaction are 0.0020 moles of hydrogen ions. So now let's calculate the pH of the solution based on how many hydrogen ions are left over. And I'll use a different color for this. Okay. So remember I told you earlier that as we're adding base, we're changing the volume of the solution. So at the very end, we can calculate the concentration using the new final volume. All right, so the concentration of the hydrogen ions will equal the number of moles divided by our new total volume. So we said that we started with 25 milliliters of solution, and if we convert that to liters, it's 0.025 liters. And then we added 5 milliliters, which converted to liters is 0.005. So that's our new total volume. So overall we have 30 milliliters or 0.03 liters of solution. So the new concentration of the hydrogen ions should come out to be 0.067 moles per liter. Okay, so let's calculate the pH based on that concentration. So the pH should be 1.18. All right, so this solution is still pretty acidic, even though we added some base. So in the next step, let's see what happens if we add 10 milliliters of solution and if we add 20 milliliters of solution. So we're still going to assume that we're starting with 0.0025 moles of hydrogen ions. But let's figure out now how many moles of hydroxide ions we're adding to solution. So if we add 10 milliliters of our NaOH solution, again, I'm going to convert that to liters and then multiply that by the concentration of NaOH, and I'm just going to write hydroxide here since they're pretty equivalent. And the number of moles of hydroxide ions should be 0.001. Okay, so now let's write that same table that we wrote before. And again, before we add any base, we said that we had 0.0025 moles of hydrogen ions. And then we're going to add, in this step, 0.001 moles of base. Now, you might be a little confused at this point because technically we already calculated the pH if we add 5 milliliters. And in this step, we're really only adding 5 more milliliters of the hydroxide solution. But when we're doing these calculations, we pretend that we're starting from 0 again. So in the second step, we're assuming we haven't added any base, And then we're going to calculate the pH based on if we just added 10 milliliters of NaOH all at once. And then in the next step, we're going to calculate what is the pH if we added 20 milliliters all at once. So eventually what we'll do is graph all of this data and we'll kind of see what it looks like. So if you were a little confused about why, we're assuming we still have 0.0025 moles of hydrogen ions when we just calculated that change. Again, we're just starting from the beginning, and then we're pretending we haven't added any NaOH yet, and now we're adding 10 milliliters all at once. Okay, so if that's the case, after the reaction between the hydrogen ions and hydroxide ions, we won't have any hydroxide ions left over because all of those hydroxide ions will get used up. And then let's determine how many hydrogen ions we have left. So we're going to subtract 0.001 from 0.0025, and we should end up with 0.0015 moles of hydrogen ions after this reaction. Okay, so now let's calculate the pH for this solution, and that depends on the concentration of hydrogen ions. So we said that we would have 0.0015 moles of hydrogen ions in solution after they all react, or after they react with hydroxide ions. Now we need to determine the new total volume. So again, we started with 0.025 liters of solution, and then we added 10 milliliters of sodium hydroxide, which if we convert to liters is 0.01. So our new total volume is 0.035 liters. And remember, we need the volume to be in liters so that we can actually calculate the molarity, which is always in units of moles per liter. Okay, so once we calculate the concentration of hydrogen ions, we should get a value of 0.043. So now the pH is the negative log of 0.043, and you should get a value of 1.37. Okay, so the pH has increased a little bit, but it's still pretty low. So now we're going to do the same thing for the addition of 20 milliliters of our NaOH solution. And again, remember, we're pretending we're just starting from the beginning, and we're pretending that we're adding 20 milliliters all at once. So again, we're going to assume that we're starting with 0.0025 moles of hydrogen ions, and then let's see how many moles of sodium hydroxide we're adding if we add 20 milliliters. So again, very similar to before, we're just changing some numbers slightly. Okay, so when we perform this calculation, we should find that we have 0.002 moles of hydroxide ions that we're adding to solution. So in the next step, we'll write out that same table that we did before. Okay, so before we added any hydroxide ions, we have 0.0025 moles of hydrogen ions, and then we're going to add 0.002 moles of hydroxide ions, and again, all of those hydroxide ions will react with acid, So at the end, we won't have any hydroxide ions. And let's determine how many hydrogen ions will be left over at the end. So we'll subtract 0.002. So we should end up with 0.0005 moles of hydrogen ions left over after the reaction is complete. Okay, so now let's calculate the pH. Same as before, but this time we have 0.0005 moles of hydrogen ions. And our total volume is 0.025 liters plus 20 milliliters, which converted to liters is 0.02. Oh, sorry. So that means that our new total volume is 0.045 liters. Okay, so let's determine the pH, the concentration would be 0.011 moles per liter. So now we can determine the pH. So if we take the negative log of 0.011, we get a pH of 1.95. Okay, so the pH has increased a little bit more compared to the last addition of NaOH, but it's still pretty low. Okay, so let's see what happens if we add 25 milliliters of NaOH solution. So same process as before. We're going to assume that we're starting with 0.0025 moles of hydrogen ions, and then we're going to calculate how many moles of hydroxide ions we're adding to solution. So from this calculation, you should find that we're adding 0.0025 moles of hydroxide ions. So you can see that the number of hydrogen ions is equal to the number of hydroxide ions. So this means that we have reached the equivalence point. All right, so let's still step through the calculations that we've been doing because I want to show you what happens at the equivalence point. All right, so before addition of hydroxide, again we have 0.0025 moles of hydrogen ions. And we're adding 0.0025 moles of hydroxide ions. And then after the addition, or the reaction, we won't have any of the hydroxide ions left over. And we also won't have any of the hydrogen ions left over because they're going to completely react with each other. So all we're left with is water. And what is the pH of water? So water is neutral, so the pH is 7. Now, this only works for strong acids and strong bases. What we'll see later on is when we're using a weak acid or a weak base, the equivalence point pH might change slightly. Or, for instance, like we saw earlier, if you have an acidic salt solution or a basic salt solution, that will also change the pH at the equivalence point. But in this example, we're using a strong acid and a strong base, so the pH at the equivalence point is 7. Now, what happens after? So let's add 30 milliliters. So again, we're starting with 0.0025 moles of hydrogen ions. And we're adding 30 milliliters of our 0.1 molar solution of sodium hydroxide. So that should give us 0.003 moles of hydroxide ions that we're adding to solution. Okay, so let's write out that same table. So before addition, we have 0.0025 moles of hydrogen ions. And then we add 0.003 moles of hydroxide ions. So at this point, you might notice that we have more hydroxide ions than hydrogen ions. So in this step, all of the hydrogen ions will get used up first. So we're actually going to end up with 0 hydrogen ions past the equivalence point. So let's determine how many hydroxide ions we have left. So we should have 0.005. Oh, nope, 0.5. There's one more 0 in there. 0.005 moles of hydroxide ions. So now we're going to calculate the pH based off of those hydroxide ions that are left in solution. So let's calculate the concentration of the hydroxide ions. So we have 0.0005 moles, and the new total volume is 0.025 liters plus 30 milliliters, which is 0.03 liters. So we have 55 milliliters, or 0.055 liters. And the concentration of the hydroxide ions should be 0.009 moles per liter. Okay, so if we calculate the pOH, we get a value of 2.04. And then remember, we can always determine the pH from the pOH because pH plus pOH equals 14. So we're just going to subtract the pOH value from 14, and that will give us a pH of 11.96. Okay, so the pH drastically changed. If we go back a couple of steps, we saw that the pH before the equivalence point was 1.95, so almost 2. And then at the equivalence point, the pH is 7. And then we added 5 more milliliters of NaOH, and now the pH is 11.96. So we're at that really steep part of the titration curve. All right, so now the last couple of steps, I would like you to try these on your own and just make sure that you get the same answers that I do. So you should find that after adding 40 milliliters of the NaOH solution, the pH is equal to 12.36. And then after adding 50 milliliters, the pH is equal to 12.52. So just make sure that you get the same answers and that you're doing the calculations correctly. And now let's graph all of the different pH values and volumes. So remember that the titration curve we saw before had the volume of titrant, in this case NaOH, added in milliliters, and then the y-axis was the pH. So since we're adding between 0 and 50 milliliters, maybe I'll go up by fives. So 0's over here, and then 5, 10, 15, 20, 25, 30, 35, 40, 45, 50. Maybe we'll do that. I probably could have spread it out more, but we'll get the same idea. And then we'll just go up in increments of 1 for pH. Okay, and then I'll change the color here. Oh, no. All right, so we said that after the addition of 5 milliliters of sodium hydroxide, actually, let's start with 0.0. So we said our initial pH, where we just had acid, was 1. So we'll start there. We had a pH of 1, and we had not added any volume of NaOH yet. And then after we added 5 milliliters of the NaOH solution, the pH was 1.18, so maybe just a little bit above that. And then after 10 milliliters were added, the pH was 1.37. And then after 15 milliliters, oh wait, we didn't do 15, we did 20. So after 20 milliliters, we had a pH of 1.95. And then at 25 milliliters, we had a pH of 7. Okay, so that's going to be right here. So that drastically changed. And then after that, we added 30 milliliters, and the pH was 11.96. And then we added 40 total milliliters of solution, and the pH was 12.36. And after adding a total of 50 milliliters of NaOH solution, the pH was 12.52. Okay, so let's connect all of these dots. All right, and we have a very similar curve to what we saw before. Okay, so hopefully this helps a little bit with understanding titration curves. I know I kind of threw it at you in Lab 1 and didn't really explain it too much, but I wanted you to kind of work with titration curves before we dived into the extreme details of titration curves. So next, we're going to work on weak acid and weak base titration curves. So I will see you in the next video.